use Descartes' rule signs to determine how many positive or negative possible zeros you could have, right? His rule sign says that in P of X, you're going to look for variations in sign. And we can do a couple of these if we need to. But this is a +2 and this is a +5, right? So that's not a variation. This is a +5, but that's -1, right? So from that sign, for that term to that one, you have a sign change. And then from -1 to -8, no sign change. -8 to -7, no sign change. That makes sense? Okay. I think some people are doing this. They're like looking at those two, and then they look at these two. Okay. And it kind of makes you get stuck when you get to -7 because there's not two things to look at. What you're going to do is it's kind of like an overlap kind of idea here. I'm going to look at these two, and then I look at those two, and then I look at those two, and then I come back and I look at those two. Does that kind of make sense? So there's always going to be, you know, this one here gets shared by two comparisons. But here we see only one sign change occurring right there. So what that means, when we look at P of X and there is only one sign change, that tells us that's how many positives possible zeros we could have. We could have one, and then the theorem says, or remove an even whole number. Well, if I remove an even whole number from 1, I get -1, right? Remove 2 from it. So you can't have -1 possible zeros, okay? Because we're looking for a collection of objects here, right? And you can't have negative objects, okay? So 1 is an only option there. The second part says number of negative zeros possible. Number of negative zeros possible. So when we look at the number of negative zeros, we actually have to determine what P of the opposite of X looks like. So I'm going to kind of write this out, and then we will evaluate it. Seriously, don't understand this eraser. So 5, -x to the 4th, minus -x cubed, minus 8 times -x, and then we got our -7 over there. Evaluating this thing, then we get, you know, that's going to be a positive x, right? Right, it's the 6th power, so it's going to be 2x to 6th. This is going to be positive as well, so plus 5x to the 4th. This is negative, but then when you have this negative inside here, or out in front, it's going to be positive x cubed. This is a negative x, but you got a negative out here, so it's going to be a positive 8x. And then there's nothing to change that -7. So as I go through this, no sign change, no sign change, no sign change, but there you got a sign change, right? Those last two, you got a sign change. So you got one sign change in the P of -x. So that tells you then that you have that many negative possible zeros, or that number remove an even whole number. So remove 2 from that again, and you get -1. So our only option then is to have one negative real zero. Okay. Now, the last part says number of real zeros possible. Well, if I could potentially have one positive zero and one negative zero, then add those together, you get 2 total, right? Okay, so that last one is just asking to sum them together. But that last one, we also have the idea, because a lot of you probably aren't getting just 1, 1, and 2, are you? Or is there another one of these questions below it? So when I do this one, we would go through, if we look, I'm just doing P of X right now. Go through that, you get a sign change at the first 2 terms, you get a sign change in the second and third terms, you get a sign change between the third and fourth terms, you get a sign change between the fourth and fifth, one between the fifth and sixth, and one between the sixth and seventh. So there's 6 total sign changes, right? So that tells you have that many positive zeros. Or remove an even whole number. So when they say remove an even whole number, it just means start removing multiples of 2 until you get down to 0 or a negative number. Okay? So start with 6, remove 2 from it, you could have 4. Remove 2 from that, you could have 2. Remove 2 from that, you could have 0. And if I remove 2 from that, I get to the negatives, right? I can't have negative values to it. So 6, 4, 2, and 0 are my only positive possible zeros. Okay. When I look at the number of negative zeros, I'm not going to do it. I'm going to write this out, but you would find out that in P of the opposite of X, you end up with all plus signs throughout that polynomial. So there are no sign changes. So there would be no negative zeros. Okay. So then they would ask, what is the number of possible zeros that you could have here? Okay. What you do is you take each one of these up here, and you add it to each one of these down here. So 0 plus 0 would give me 0. 2 plus 0 would give me 2. 4 plus 0 would give me 4. 6 plus 0 would give me 6. Right? If this was, say, like 2, 0, and 2, then you have this list of 0, 2, 4, 6. And then you also have this list of 0 plus 2, which would give me this 2 again. You go 2 plus 2, which would give me that 4. You go 4 plus 2, which would give me that 6. And you go 6 plus 2, which would give me one more possible total of 8. Which makes sense because that's an 8th degree polynomial, right? So that could happen. So just keep that in mind. I don't know. I'm going to venture to say that because this is the only number that changes, and I'm assuming that they probably left it as positive for everybody, that everybody probably had this answer, regardless of what their polynomial looked like. But if there are additional ones here, you have to add both lists together. Is that doable? Okay. Any others? Any of the last class asked about some of these. It asked you to find all the zeros and then to graph it. You know, you want to talk about? My hope is, you want to talk about one of these? Okay. My hope is that we're not typing that into like Y1 and getting the answer and matching the graph up, getting the answer that way, and zooming through that, right? I mean, you can do that. You can get the right answer. You can get the points on the test or the quiz, and that's the homework. But if you're to do that on the test is going to ask you, show your synthetic division, show your work for credit. If you just match this stuff up to a calculator, that's not really the best approach. So we'll do one of these. Give me, looks like everybody had the same question. Did all yours, everybody got theirs open? It looks like there's nothing red here, so it looks like this is kind of a static problem, not changing for everybody. So we can do that. Actually, let's go up and do, so we did that one in the last class, so that'll be posted online for you. Let's do this one. This one's different. So question 16. All right, so they ask you to look at that, find all the real zeros of P. So, the first handful of questions in the assignment were kind of getting you to be able to find that those are, the factors of that are going to be your P values, right? So factors of 45 plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, and then plus or minus 45, right? Okay. We look at our 1 out here. That's our Q. The factors of that are our Q, so plus or minus 1. When your A term is a 1, then your P over Q's are identical to just your P, right? Aren't they? Oh, did I forget 9? Okay. All right, so your P over Q's are the same thing as that list there, okay? So let's see if we just cut and paste that. Come on. All right, so those are P over Q's. I don't know. So now we go and we test those, okay? Remember what the theorem says. These are just potential zeros. We could have all three of them can show up in this list, and you are seeing that with the answer here. But it could mean that one shows up, could mean that two show up, could mean that none of them show up. Okay, these are just places to start, okay? So we write our synthetic division out. We're going to write our coefficients of 1, -5, -9, 45. Make sure that you put placeholders in of zeros if they exist for particular powers of x. And then we just start. I've told you that you can use your technology to give yourself maybe a head start on how to do this. I'm going to just blindly start working through this. Hopefully you don't do this on a test blindly, because it might not be to that 15 that I find a zero, and I've done 4 synthetic divisions or 6 synthetic divisions before I find that I've wasted a lot of time. Does that make sense? So hopefully on a test we use our technology to help us out, to at least get the ball rolling, get a start. So 1 times 1 is 1, -4, -4, -13, and then -13, and that gives me, what, 32? Now, looking at that one, the reason I want to try some of these is because I want to see if, when I used a positive number, okay, the upper and lower bound theorem says with a positive number up here, if you get all positives down here, if you get all positives or zeros down here, you can say something about that 1. Okay, here we don't get that, so really the only thing we gain from this iteration of division is that 1 doesn't work. Okay, you guys know what I mean by iteration? Okay, doing something repetitively over and over, each one of those actions is referred to as an iteration. So that was one iteration of division. We'll do another iteration with -1. So then I bring my 1 down. -1 gives me -6, gives me 6, gives me -3, gives me +3, and 48. Again, not a zero, and with a negative here, we're looking for this last row to alternate in sign. And it doesn't do that. So only thing it tells me, -1 doesn't work. Okay. So then I go to, I think most people will probably go to +3 next, but I'm going to go to -3 just to kind of prove a point here. If I go -3, bring my 1 down, multiply gives me -3 there, add gives me -8. That gives me, what, 24. Add together gives me 15, and then I get -45, and then that gives me 0, right? Okay, this is nice because, 1, it tells me that that is a 0. -3 is a 0. But it also tells me some other things about my list. Because this is negative, and this is a positive, a negative, a positive, and I can let 0 be anything I want it to be, so let's let it be a negative. Does that last quotient line alternate in sign? So that tells me that -3 not only is a 0, but it's a lower bound. So if I am doing this entire thing by hand, and I have no calculator, or I have no understanding of a better way of doing this, I can at least use this theorem and say, now you know that you don't have to try -5. You don't have to try -15. You don't have to try -45. And you don't have to try -9. That just eliminated a lot of things out of your list, right? Okay. You can then keep going with synthetic division if you want to. Okay. Try 3. You'll see that when I try 3, that thing breaks down even further, right? I get another 0 when I try 3 with 1, -8, and +15. My suggestion, though, just because it's going to save you time, you knew this was x cubed, right? Divide by a linear factor of x. This is going to become what? X squared. When you get a quotient line that is x squared, stop all synthetic division. Okay? Because when we're doing the synthetic division, we're kind of just throwing a dart at a dartboard and hoping it sticks, right? We don't necessarily know which values to choose. I know that when we get down to x squared minus 8x plus 15, we have a definitive set of rules that will always provide us the factors of that quadratic, okay? Where it's no longer a guessing game like synthetic division was. So I'm going to take that quadratic and factor, okay? Two numbers I multiply together to give me 15 and add up to give me negative 8. X minus 3 and x minus 5, right? Okay, and hopefully you realize that that's a little bit quicker than even doing the synthetic division, even if the synthetic division works right away with the next value you chose. So we see that positive 3 and positive 5 are zeros as well. And if I wanted to rewrite p of x, I don't know if they asked this on this question, but if I wanted to rewrite p of x in factored form, it's going to be x minus 3, x minus 3, x minus 5, or maybe you see some exponent stuff here. We got x minus 3 squared times x minus 5. That works. Okay. And then they want you to graph this thing. Okay, or choose a graph. Which, like I said, if you're using your calculator, you probably know what your graph looks like, and that's an easy choice. But if we kind of think about everything we've done so far in this chapter, we should be able to get a pretty comprehensive graph. Think about what we just found. If we found the factors or the zeros, okay, because they're related very strongly, I should know where we cross the x-axis, right? Vince?
Can you take x minus 3 squared because there's a negative and a positive 3?
Oh, were they?
Yeah, there should be x plus 3 and x minus 3.
Oh, my fault. My fault. Good call. So this one of these was a plus. Yeah, so you can't do that. That doesn't make any sense. My apologies. I'm sorry. I do want to come back to that though. So when we're done graphing this one, I do want to come back to that idea because it tells us something about our graph that is different than this one. But if we know our factors, it tells us our zeros, right? So our zeros are 3, 5, and negative 3, right? Okay. If I look at my original polynomial, it's cubic, right? Do you know from section like 3.2 what the end behavior of that looks like? It's a positive cubic function. So as x goes to positive infinity, y is going to go to positive infinity. As x goes to negative infinity, y is going to go to negative infinity, right? Okay. We also know by looking at the original polynomial that your y-intercept is what? 45. Okay, so obviously this won't be to scale, but let's say that's 45. Now, all of those zeros had a multiplicity of 1, right? Multiplicity of 1, multiplicity of 1, multiplicity of 1. So that tells me then that I should be able to start down here, come through here, okay? Now, I've got to touch my y-intercept, right? Before I start coming down back through this other 3. Now, I don't know if I reach my maximum to the left of 45 and then come down through it. Does that make sense? I don't know that I hit 45 and that is my maximum. And I don't know that maybe I pass through 45 and then my maximum comes after it. Does that make sense, everybody? So you got some options that could happen there. And we'll see when we graph this with technology what the result really is. But maybe I graph that one, okay? But now I'm going to come down through 3, right? Come down through 3, and now I've got to do what? Back up through 5. So I know I'm going to hit a minimum, right? Now I don't know how low that minimum goes, but then I go through 5, and I know my end behavior is going to tell me that you keep going that direction, right? Okay. So the idea then is once I have that image in my mind, or I've done a quick sketch of it, I could then match that up on WebAssign to the one that they're looking for. Okay. So going through 45, so we went through what were our x-intercepts? 3 and 5. So we're looking at it's this one here, right? 3 and 5. End behavior is the same. End behavior is the same over here. X-intercept. Sorry. X-intercept positive 5, positive 3, and negative 3. Okay. If we did go through something like I at the beginning, I mistakenly had this as x minus 3 squared, right? What would that tell you about the 0 of 3? Okay, so it would just bump it, right? Okay. And hopefully maybe this, if you would have done this incorrectly like I did, you would have figured out this doesn't really make a whole lot of sense, because if I've got to be in behavior and I bump at 3, okay, 5 has got to be my other 0, right? So, and it's a multiplicity of 1, correct? So I had to go through it and keep passing, right? So does that contradict the in behavior that I initially thought I should have? Yeah, okay. I guess not, because I could do this. If 3 could be tangent there, right, beneath it, and then come back up through 5, so it could look like that. But what I want you to understand is the multiplicity. The multiplicity is going to provide either tangency or you pass through both planes to help reconfirm the things we talked about in sections 3.1, 3.2, 3.3. Does that kind of make sense? The one we did last period was this one here, where you, and like I said, everybody's was the same. We go through the synthetic division, we get these zeros, okay? And we get -1, 2, 2, and 2, right? And that's a multiplicity of 3. So it's an odd multiplicity, so you pass through at 2. You know it's an x to the 4th, so the end behavior has got to be, as x goes to positive infinity, so does y, okay? And we know that our y-intercept is -8, okay? So this one has the end behavior information. It has the y-intercept information, but the zeros are kind of backwards, aren't they? Okay, so that's not the one we want. This is the one we want. We have the end behavior. X goes to infinity. Y goes to infinity. You have at positive 2, that 0 that had a multiplicity of 3. You see that you pass through it, right? Now, what's kind of interesting to kind of think about is that you don't pass right through it. Like look at -1, how that line, that portion where we're passing through -1 looks very linear, right? The higher the multiplicity, that root is going to look kind of like, since that's a multiplicity of 3, at that root it's going to kind of look like a cubic does. Okay. If it was a multiplicity of 2 or 4 or 6, then it's going to look like the multiplicity of, that feature of that graph is going to look, if it's a multiplicity 2, it's going to look quadratic in that neighborhood, okay, at that 0. If it's to the 4th, it's going to look quartic at that point. Does that make sense, everybody? So just focusing simply on the multiplicity kind of gives me more than just the idea that I'm passing through, but it gives me, in addition, kind of what it looks like in that kind of viewing window. Okay, that we're not passing through in a linear fashion. It's very cubic in nature. Is everybody okay with that? Okay. Not something that the text ever talks about. Not something that I'm going to force you to kind of mimic on a handwritten test or anything like that. But it is a feature that exists that might be important to talk about. Important today. Huh? It is. No, they're probably like, don't come home.
Don't come home.